So let's move on with our proof. So the side just gives us the idea. Let's actually go through the mathematical proof. So proof. So we start out by saying let n be a particular but arbitrary integer. So now, here's the thing, right? We never work with integers or like full-blown integers. In our aside, we either worked with evens or odds. That's okay, right? Because every integer is either even or odd. So they form a partition is what it's called. So what I can say is note n is either even or odd. Proceed by division into cases. Uh-oh. I mean, what's the opposite of uh-oh? Yay. Oh, I don't know. The point is we talked about division in cases before, right? This is one of our argument forms. This is what I was talking about, where this kind of stuff is always under the hood. So I'll say case 1, consider n even. So basically what we're doing right now is we're doing the division in cases argument form, where we have like for all n z, right, n even or n odd. And then if we can show that n even implies n squared plus n even, and if we can show n odd implies n squared plus n odd, we can conclude by division into cases that n squared plus n is even. So that's what we're doing under the hood. So it all comes back. It's all there. I swear to you, it's all there. So we don't need to write any of that though. So case 1, consider n even. What do we say if n is even? Then by definition of even, there exists a k and z such that n equals 2k, right? Then n squared plus n is going to equal 2k squared plus 2k by substitution, right? All it's saying is every step here we're going to justify, right? And so n squared plus n equals 2k squared plus 2k by substitution. We're justifying why we can do that. We can do that because n literally equals 2k, so we can substitute out for each other. All right. Actually, we don't need that. And then what's this going to equal? Well, and this is going to equal plus 2k. We're going to distribute that exponentiation by distributing exponent. Then this equals 4k squared plus 2k by evaluation. We're really writing every step. You're just evaluating 4k squared to get that. And this is going to equal 2 times 2k squared plus k by factoring. Right? So I've talked a long time. How do we end this proof? What do we what do we do? We're so dang close for case 1 at least. How do we put it to bed?
We show that like an even is just anything, 2 times anything.
Exactly, right? So it's 2 times anything, but that anything has to be an integer, right? That's an important step we can't skip. Because if we just got to 2, if we were doing a different proof, we got down to like, oh, x equals 2y, therefore x is even. Well, what if y was like 0.5 or something like that? What if y was pi? You know what I mean? We have to be a little careful, right? We're not leaving any stone unturned here. So note that since 2 and k are in z, and z is closed under addition and multiplication, 2k squared plus k is in z. Make sense? In the closed thing we talked about last time, that's just things you can assume, right? Like our few assumptions we started with is that the integers exist, we know what they are, and they're closed under addition and multiplication. Then we have that thus since 2k squared plus k is in z, by definition, 2 times 2k squared plus k is even. This is where a lesser man would say boom shakalaka, but I'm just going to say any questions. So are we done?
No.
We still have a whole other case left, right?
Yeah.
Only
Right,
half
yeah.
of the integers.
We got half the integers, right? Which, hey, that's a decent percentage, all right? 50% is better than 0. If you just proved it for 100 integers, that would represent 0% of the integers. It's better than that, right? But anyway, yeah. So we've proven for half, right? So we've proven that part of the division into cases where if n is even, then you know that n squared plus n is even. Now if you do the other part in division into cases. So in a normal proof, this will all be on one sheet of paper. So keep this in your sheet of paper. I'm going to pretend we're scrolling down and doing case 2 now. So let's do case 2. And I'm going to breeze through this a little bit because we kind of know it. Because it's kind of the same. Case 2. Consider n odd. Then by definition, there exists a k in z such that n equals 2k plus 1. Then n squared plus n is going to be 2k plus 1 squared plus 2k plus 1 by substitution, which then, or I'll say, actually, to save us a little work and show you how you do this, right? We can always use theorems. You can always use any theorem or anything to prove in class. So I'm going to use what we did in last class. So note, by proof last class, the square of any odd is odd. Thus, n squared is odd. So by definition, there is some c and z such that n squared equals 2c plus 1. Because to be odd, it means u equals 2 times some integer plus 1. Then n squared plus n equals 2c plus 1 plus 2k plus 1 by substitution, which then equals 2c plus 2k plus 2 by addition, or I'll say by evaluation or by simplification. Here, simplification, evaluation, that all just means you're just doing some math, right? You're just adding two things together, that kind of thing. But then this equals 2 times c plus k plus 1 by factoring. And now we're in the same spot we were before, right? C plus k plus 1 is an integer. Why do we know c plus k plus 1 is an integer?
Is it because we know that c is an integer and we've defined k definitionally to be an integer for our case?
Exactly. We define c to be an integer. Right, where is it? Right here. C by definition is an integer. K by definition is an integer. 1 is an integer, right? That's the one thing we're sure of in this life. So then c plus k plus 1, since the integers are closed under addition, are integers. So then, I'll say note, since c, k, and 1, and z and z is closed under addition, c plus k plus 1 is then z. Therefore, 2 times c plus k plus 1 is even by definition. And we're so close. All we're going to put after this is one little line basically saying, and this closed out this case. Hence, since n squared plus n is even in all cases, n squared plus n is even for all integer n. Box, close it off. Done. Come on, people. Come on. I mean, right now, what we just did, right, is what we, like the same thing we did last time. We just proved something about infinitely many things. Well, I mean, there's kind of a lot of lines, but not infinitely many lines, right? This could fit on one sheet of loose leaf, right? We just proved this fact that we might have been taking for granted our whole lives. Like, we might have thought it's true our whole lives, but we didn't actually know. This is the weird thing about math. It actually allows us to know, to be certain on a really, really deep level that we almost don't have in any other aspect of our lives. Any questions? Like, this is almost inarguable in the sense that even if you had the best lawyers in the world, trying to break apart this argument. They wouldn't really have anywhere to go. The only real place it has to go is say like, why are the integers closed under addition? Because that's our assumption. And then I could show them some sort of set theory proof that would come down to it, but then they go, why does that work? And I go, okay, because I guess we assume things exist. Like, it has to come down to that kind of level. But anyway, any questions on this? All right. Well, that is a universal proof using the direct proof method. Pretty fun. We're using a lot. Note, by the way, that this level of detail I'm showing is expected in homeworks and tests and things like that. This won't be on your test on Wednesday, by the way. This is all stuff for, this is all new stuff. But for the things going forward, this level of detail is kind of expected. You need to justify every step like that. You need to say that the integers are closed under multiplication, claim, formal, all that kind of stuff.